of equal mass that is rotating around a fixed point by two strings, and we asked what happens if the string snapped. What we found was if our initial angular velocity was omega, these two masses had two properties after the snapping of the string. They actually turned with a frequency which was equal to the initial rotation frequency, and the center of mass velocity was omega times 3/2 L. I found these two results by energy conservation and momentum conservation. But let's check if I'm actually correct here. If my definition of angular momentum is correct, angular momentum should also be conserved in this problem. Once the rope is snapped, there are no external torques on the system too. So what is my initial angular momentum? I can say that this first guy is moving with v, which is omega times L. So r cross p, that length is L. R cross p for that mass is r is L, p is m times omega times L. That's coming from the first mass. From the second mass, I'll have 2L, so V2 will be 2L omega. So I'll have 2L times m times omega times 2L. Overall, I'll have 5m omega L square. How about in the final situation when these two masses are rotating and moving away? What's my V center of mass? We have found it. So, okay, let's first calculate I center of mass for this configuration. I have two masses which are a distance L over 2 from the center of mass. So this is going to be 1/2 ml square. So final angular momentum is, let's do it like this. I center of mass is ml square over 2 times omega prime plus, now what is according to the same point? I have to take it according to the same point. What's r? Well, theta is that angle. R sine theta is 3/2 L, and total mass is 2m. Total velocity, center of mass velocity, is 3 over 2 omega L. So let's calculate everything here. Omega prime is omega, so 1/2 m omega L square plus, what do I have here? 9/2 m omega L square. So overall, I have 10 over 2 m omega L square, which is equal to L initial. Okay. So we have one problem here where both angular momentum and energy were conserved, and thankfully they are conserved in such a way that all three give me the same result. So I could have solved this problem without invoking energy conservation or momentum conservation. I could have done away with one of them if I used angular momentum conservation. Let me, before I go to the solution of the quiz, let me spend a few moments about units again. My favorite subject, right? I really like it. So angular momentum, we said, is R cross P. What's the unit of angular momentum? Well, R has units of meter, momentum have units of kilogram meter per second. Kilogram meter per second. So this is going to give me kilogram meter square per second, which is, I'll write it in a slightly different way. Kilogram meter square per second, square times second. Or joule second. Oh, wow, that's kind of strange. But that's the way it is. And it doesn't get a special name, thankfully. But here's the thing. L, or angular momentum, is quantized. That's extremely surprising. But it turns out when two objects interact with each other, they can exchange angular momentum only in units of a fundamental constant. There is a fundamental constant which we call Planck's constant, and show it, well, Planck's constant is h, but h over 2 pi is the angular momentum unit that's actually used. It's called h bar. Now, this is very strange. Do you remember when I talked about, well, we haven't talked about electric charge, but you know that all electric charge in the universe comes in integer powers of electron charge, E. So you get 2e, 3e, 5e. You never get fractional charge. Yes?
How about electrical load of quarks?
Quarks, that's a very good, it's 1/3, 2/3. And that's why you never can see an isolated quark. Quarks cannot be isolated from each other. They always come in bunches which give me either 0e or 1e. Okay, so that's actually a good one. So you cannot have isolated electric charge that's different from n times electron charge. And that, it turns out, is the same for angular momentum. Now, when we actually, draw some electricity, so some current from our outlet, we don't count the number of electrons. We will invent other units like amperes, right? So we treat electron charge as if it's actually a continuous quantity, as if it's a real number. Why is that? Because the charge of a single electron is extremely small. Okay. Similarly, it turns out Planck's constant is very small compared to our natural scales. Our natural scales is, joule is something pretty much, if I move my arm, it gets kinetic energy of 1 joule, and 1 second is the time scale that we are available with. H bar, it turns out, is 10 to minus 34 joule seconds. Okay? It turns out in daily considerations, when I'm rotating around in my chair, my angular momentum is quantized. I know that. But I can't treat it as a continuous quantity because h bar is so small. Nonetheless, when you go to the atomic level, when you go to the nanoscale, if you want, angular momentum quantization is extremely important. It turns out, for example, the light coming out of atoms carries some signature of the angular momentum of the electron. So, it turns out the angular momentum of an electron inside an atom, it can have, so angular momentum of this electron can be either 0 h bar, 1 h bar, 2 h bar, 3 h bar. Okay. It cannot be 1.5 h bar. And somehow, I know that there is a chemistry exam coming up for most of you. You actually know this, but you call these things with other names. Instead of talking about the angular momentum of the electron, you call these as s orbitals, these as p orbitals, these as d orbitals, these as f orbitals. Okay? And why did this come true? Because people did not understand that quantization is related to angular momentum for a long time. They could see it in the spectra of atoms. They heat these atoms up, some light comes through, and these come from spectroscopy. So these are orbital names. If the light coming from an atom was sharp, that was called an S state. If it was principal, I don't know what that means. Okay, but that's usually the most shiny thing, shiny light. That's coming from P level. If it's separated out, that's called diffuse. I think F is called fundamental. And I think the spectroscopists, the chemists, run out of creativity at that point and just revert back to the alphabet after that. But nonetheless, I think for those of you who are going to take a chemistry exam, it's nice to know the historical, the background for these strange letters. Yes?
If the electron in the s orbital has a zero angular momentum,
Yes.
so we can say the electron is actually not turning around.
It's not rotating. You're correct. Yes. So all the picture you think about electron rotating around the proton or nucleus is somewhat wrong. So we need to tear down all those classical concepts and start with talking about the wave function and quantum mechanical nature of the atom. All right? Good. So I'll also tell you one more thing, how important angular momentum is, how important this quantity h bar is. It basically measures the importance of quantum mechanics in your system. Okay, h bar is a measure of that. You'll see, maybe you've already seen, that the uncertainty in the position of an object times the uncertainty in the momentum of the object. What's the unit here? This is meter. This is kilogram meter per second, which means joule second. This must always be larger than h bar over 2. Similarly, you'll see that the uncertainty in an energy measurement times the uncertainty in time measurement. What's the unit? Joule second. This must be, well, it's not as a hard limit as the other one, so it's approximately must be larger than h bar. Okay. So these are called uncertainty relations. Those of you who are in the physics department will take a course in modern physics next year, spring. We'll study these in more detail, and certainly in quantum mechanics. Chemists, there are a lot of chemists in here. They'll take quantum chemistry, they'll study these relations more importantly. But you see, fundamental constants are important. We have speed of light, c, which allowed us to define meter, right? That was very good. Similarly, I told you that second can be defined in terms of some oscillations of cesium, which is more or less, it's not exactly a fundamental constant, but it's something that appears in nature. It's easy to replicate. And now, people are trying to base our third basic unit, kilogram, on Planck's constant, h bar. Okay. So Planck's constant is something that can be measured quite accurately. It would be great if we can turn that accuracy into the accuracy of mass measurement. All right? Question.
Why you don't use length as a times of Planck constant? For example, 10 over 5 plus Planck multiplied by Planck constant. You can use this as a length.
H bar has units of energy times time.
I'm talking about a meter version of Planck constant.
There is no meter version. That's the problem, right? You need a quantity which has the correct units and is a fundamental constant. Yes?
So, what's I'm interested is that mass will be measured in terms of
Loudly, please.
mass will be measured in terms of joules per second.
No, you need something that normalizes it, essentially, okay? So what basically that turns into is turning, you can define the mass in terms of an atom's mass, and there h bar comes into play, okay? You'll have to learn a little bit more of quantum mechanics to see how this definition can be shifted onto the mass, okay? Mass definitely will not be measured in terms of angular momentum, okay? So that you need some clever experiment to shift the uncertainty in h bar to the mass measurement, okay? So far for Planck's constant. Let's go back and let's solve the quiz, okay? That was quiz 22, right? I think your assistant has mixed the order of the quizzes, so don't worry about the quiz order. I got an email, right, about the order of the quizzes. Don't worry, all of your quizzes are going to be graded before the end of the term. So here I have a nice rod of length L and mass M, and it's tied from two different points. From one edge and L over 4 from the other edge, right? So first order of business is to find T1 and T2. Now, how do we do this? Very simply. We know that we have the free body. We draw the free body diagram for our rod. We draw the free body diagram. Here is T1. Here is T2. What else? What's the third force acting on this system? It's the weight of my rod, and the weight acts at the center of mass. Center of mass is a special point, so it's going to be mg. In the static situation, is there any acceleration? No, so F equals ma, that's 0, which tells me that mg is basically T1 plus T2. Good. What else do I need? Obviously, I have two unknowns, T1 and T2. I need one more equation. And I actually have one more kind of Newton's equation for this rigid body, which is torque equals I times alpha. But in a static situation, there is no angular acceleration. So that must equal to 0. So torque is equal to 0. And here's the problem though. Torque with respect to which point? Excellent, any point, right? If I'm in a static situation, any point. But what's my rule? Which point do I like the best? The center of mass. So I'll actually stick to the center of mass, and I'll say, use center of mass. But in this problem, you could have used any point. So let's use center of mass. What's the torque of T1 and T2? Let's find these distances. This distance is L over 2. This distance is L over 4. Torque 1 is L over 2 times T1. Which way is the torque caused by T1? Is it clockwise or counterclockwise? Clockwise, right? It's trying to rotate my rod clockwise, so I'll say it's clockwise. How about torque 2? It's going to be L over 4 times T2, but it's trying to rotate my rod counterclockwise. So torque 1 plus torque 2 equals 0 actually means, as a vector, if I write this, L over 2 T1 must be equal to L over 4 T2, else cancel. T1 is T2 over 2. I have two equations, two unknowns. mg is T2 over 2 plus T2, or T2 is 2/3 mg, which tells me T1 is 1/3 mg. I'm hoping each and every one of you have found these results, right? Excellent. Now let's go to the second part, which is more exciting. Okay. Now here's the situation. Suddenly, the second rope has snapped. Okay. So what do I need to do now? I need to find two things. I know that there will be an acceleration of the center of mass, but because whichever way you look at the system, there is a torque on this, there must be a angular acceleration, right? How am I going to solve it? No magic is needed. Once again, free body diagrams. So free body diagram is very simple. I have mg acting on the center of mass and T acting up. So I know that if I'm interested in a center of mass, m times a center of mass must be mg minus T. When I'm writing linear version of Newton's second law, I do not care where these forces are applied, right? I actually put all the forces in a vectorial combination. That's great. So that's my first equation. How about my second equation? My second equation is that let me write it once again as a in the center of mass frame. So I have mg, but now I have T here. What's the alpha here? I center of mass times alpha. Is what? This is written in the center of mass frame, so it's only going to be the torque created by the rope, right? So it's going to be T times L over 2. So that's my second equation. How many unknowns do I have? T, a center of mass, and alpha center of mass. So I need one more question.
Isn't D equal to T1?
No?
It has changed.
Yes, it has changed. It's a massless rope, so when I cut it, it suddenly can actually give me supply a different. That's the most general case. Let's find out what it is at the end, okay? Good. Now I need one more equation. 3 unknowns, 2 equations. And what's that? What's the physical principle that actually tells me there must be a relation between A and alpha? Which part of this rod does not move? No. I mean, obviously the point that's actually at the edge is tied to the ceiling, right? Its distance from the ceiling cannot change. So momentarily at the initial moment, it cannot move. It's not going to move. So I will say that point is momentarily stationary, which means alpha times L over 2 is a center of mass. Okay? So it's as if all the rotation is basically around that point momentarily. Okay? So 3 equations, 3 unknowns, I can actually handle that if I know that I center of mass is ml squared over 12. So let's solve it. 1, 2, 3. In the third equation, I can write T L over 2 is ml squared over 12. And instead of alpha, I will write 2a center of mass over L. L's cancel here. I have 6, I have 3. So this is great. T is m a center of mass over 3. Now I can use it in my first equation. M a center of mass is mg minus m a center of mass over 3. So m's cancel. 4/3 a center of mass is g. A center of mass is 3/4 g, which means T is m times g over 4. So as you can see, it has changed actually. Okay. I found a center of mass. I can also find omega, well, not omega, alpha, right? Alpha is 2 over L times a center of mass. So it's going to be 3 over 2 g over L. Okay? Yes, question.
You said that the point was stationary. Why does it have to be stationary?
Okay, so here is my logic. Maybe I should explain it better. Okay, I'm saying that momentarily, okay, I have a acceleration down and an alpha, right? So a moment later, I know that this center of mass will move down by a delta, and I will have actually rotated by an angle theta, right? Now, I know the following. The distance of the edge, maybe I should do this more. I have actually rotated around the point. Okay. So the distance of the edge from the ceiling is delta COM. It went down by delta COM, but minus L over 2 times sine theta, right? For small angles, theta is small. I'm just starting my motion. So this distance must be 0. Delta center of mass minus L over 2 theta must be 0. If I take two derivatives, I'll find A center of mass minus L over 2 alpha is 0. Okay. So basically, I'm just writing the position of one edge in terms of my instantaneous acceleration and angular acceleration. I'm making sure that my edge, which is tied to the ceiling, does not move away from the ceiling or gets closer to the ceiling. Okay?
What if it moves? This way would not hold true.
I'm just saying that how can it move? Its distance from the ceiling is fixed by string. Okay? So it's that distance I'm actually considering. Unless my string extent, it cannot move. All right? If I look at the motion at later times, it will have a swinging motion. Right? But here, I don't remember if you were in the physics department, but in analytical mechanics, you can actually look at the full motion of this object and basically see that at the initial moment, you cannot give any substantial movement. Okay. Any other questions? Okay, so next time on Thursday, we'll have 2 quizzes. Okay. 1 hour, just 2 quizzes. It's extremely important that you show up. We're also going to start the new chapter, which is oscillations. That's something new. That's something you have not learned. We'll have some new mathematical tricks. Okay. Please do show up. Tell your friends to show up for Thursday's lecture. Okay. That's all for today.